Okay, so for this audio lecture, we'll be looking at fermented foods, the beverage category. So for fermented beverages, this includes wine, beer, distilled spirits. Distilled spirits would be concentrated fermented beverages, ciders, and mead. So you can see on the table here that I've included. You have your starting material, which is your source. So things like grains like barley, rye, corn, wheat, rice, and those will make your fermented beverages that are like variations of different beers or with rice sake, and then that can be further concentrated down into distilled beverages like whiskeys, depending upon what the starting material is. So bourbon is whiskey that's made from corn. And then you can have other starting materials like juices from fruits, so such as juices from apples that you can use to make cider, that can be further distilled or concentrated where you evaporate some of the liquid off, where you can make apple jack or apple brandy. Okay. You can use juices like from the agave, so you can make distilled spirits like tequila, potato. If you go down, you can make vodka with potatoes. So again, depending upon what your starting material is, and how concentrated it is, you can get different products. You'll notice that your starting material of honey, towards the bottom of that table, that's used to make mead. And mead is one of the earliest alcohols that evidence has shown. So this uses honey and water to make mead or honey wine, and we'll talk about that later on. So the first half is looking at some of the microbes involved, and then we'll look at wine, beer, and mead and how those are produced and the microbes involved. So with fermented beverages, we're looking at fermentation with yeast primarily. Definitely when we're looking at some of the more complex fermentations, it might be a mixed culture where we have bacteria present also. But the big workhorse of fermented beverages would be Saccharomyces. So we can see here with beer and wine fermentation, we have alcohol production. With beer, we also have the carbon dioxide production. We've already talked about fermentation with yeast, with Saccharomyces, with bread. So we're going to focus more on what's unique of it. I have included the chemistry of a couple different fermented beverages. These posters kind of focus on some of the different aromatic compounds, different molecules that are present that give the classic flavors to it. One of the things you may want to make note of is on the top where we have ethanol concentration, so alcohol by volume. But you will also notice that certain compounds are found throughout, so like glycerol and some of the organic acids. But again, there are also certain compounds that are unique to each of these beverages. So you can see with looking at the chemistry of wine, we're talking about 12% ethanol. And then when we're looking at the chemistry of the champagne, one of the things you're going to note is that the percent of carbon dioxide loss from champagne via bubbles is 20%, so it's higher. And then with the chemistry of beer, percentages usually being lower, around usually less than 6%. So if it's above 6% alcohol by volume, usually there's a different denotion, a naming of the beer, and you can get up to high as 9%, which are the triple E beers. But again, most beers are going to be around the 5% alcohol by volume, and many of your not home brewers, but your small like craft beers, there are some counties and states that actually mandate that they can't brew it higher than 6%. And then we have cider, and then whiskey, and then vodka is the next one. And one of the things you'll notice is that with whiskey and vodka that we have a distilling process. This allows for evaporation, and then in many cases we also have, like for whiskey, there's an additional aging, because the compounds that are found in the barrels that they're aged in gives it some of the characteristic flavors. And lastly, vodka. So when we look at alcohol fermentation, from glucose, we're going to end up getting pyruvate being formed through glycolysis, or the EMP pathway. And then we're going to get the alcohol fermentation where we convert the pyruvate into ethanol. We can also get carbon dioxide and acetaldehyde being produced. And again, this is similar to what we would see in bread. So we're just going to focus briefly on winemaking in the process. Wines fall into different categories. The major categories would be white wine versus red wine. Then within that, you can have differences based on acidity, so whether it's a dry or a sweet wine and such. So there's further breaking down, but looking at the general process with white wine versus red wine, your starting material is going to be grapes, and then they go through a destemming, crushing procedure where this is kind of where quality control. So any grapes that don't meet certain standards would be removed. And then we have a maceration process where it's further broken down. And then this is where it depends on whether you're white wine or red wine destined, whether you do a pressing or whether it's allowed to ferment. So in red wine, you can see how fermentation happens and then pressing, removing of large particles from that. Where with white wines, the larger material is removed and kind of the somewhat clearer liquid left is what undergoes fermentation. The grapes are providing the sugar source. And in many cases, you're adding bacteria in after that juice has gone through pasteurization. So you're starting with a clean slate. Okay. And then the wine can go through a second fermentation if desired, malolactic fermentation, which is due to bacterial fermentation. And what this does is actually produces more lactic acid. It removes the malate or malic acid that has a very acidic flavor to it. So by going through the second fermentation, it makes the wine have a smoother taste to it and less acidic. Not all winemakers go through that process, but some do. You then get clarification. So this is where, again, kind of like a filtration, any kind of maturing, additional flavors kind of added. And then you get a fining, sterilization. So a lot of times proteins can be added in to help draw out and finish the wine. And then you would filter those out and then it gets bottled. Now on the microbial standpoint, when we look at the process of winemaking, the wines are coming from outside at a vineyard, and so the vineyard is going to be a source of microbes that could be present on those grapes. Again, many times, many vineyards will opt to pasteurize the grape juice so that you eliminate any of that potential of a wild fermentation with these unknown organisms. Okay. So this paper just looks at how does the microbial fingerprint, if you will, of the wine change over time. And so you can see in figure 2 how what we initially see is that we get a dramatic increase in selection for yeast, in part because that may be what it's being inoculated with, but also the conditions favor that alcohol fermentation to occur by the yeast. There ends up being this increase in malic acid or malite, and so now we're starting to favor Enococcus bacteria that can undergo malic lactic fermentation. So they'll take that malite and then convert that to lactic acid. Okay, so we see this shift. There's always an underlying level of some of these lactobacillus bacteria, enteric bacteria too. So just looking a little closer at the malolactic fermentation, again, you can see how we have malite being produced, and so these bacteria are able to uptake the malite and then convert it to lactate or lactic acid, and so then they can pump that back out. In some cases, they can produce carbon dioxide also, and again, all this is going to change the flavor of the wine, so it reduces the acidity, which reduces the sourness of the wine, and will give it a smoother taste to it. So then looking at brewing, production of beer, linking this back to this information that's in the beginning of this unit, looking at where are these microbes going to come from. We can have controlled fermentation, and that's definitely more popular in large brewing companies where they're making large amounts of their beer, and where they want to control the flavors of it. So they want that reproducibility of their product. So many cases they'll have cultures that they're going to store in liquid nitrogen, or cultures that they get from a commercial site. So in that table at the bottom of the slide, you can see some of the different sources of funguses of yeast that they would purchase in order to make their beer. There's, for smaller scaled companies, there's, additional kind of at-home brewing type kits where you would add a known culture to the beer after you've heated it, after it's gone through a pasteurization. Some companies do use a backslopping technique where, again, they keep some of that, some of the microbes from the previous batches, and then they utilize those again. There is issues because of how yeast reproduce. Usually after 10 to 15 generations, there's enough of a genetic drift that you get variations. So those variations can lead to changes in the flavors of the end product of the beer. And so that's not always desirable. So most companies want a dependable product that they know their consumer is going to want. But some smaller brewing companies will use the backslop approach, and also will use natural fermentation. We'll talk about that in a little bit. So there's two different types of beer fermentation in general. So we have what's called top fermentation and bottom fermentation. So top fermentation, the Saccharomyces will actually sit at the top, hence called top fermentation. So they kind of float there at the top. This is done at a warmer temperature. And this ends up producing beers that fall into the ale, port, and stout categories. And again, there's that fermentation that's happening where those microbes are present. With a bottom fermentation, these are usually different species of Saccharomyces, and they ferment at a cooler temperature. And so the yeast actually will settle down towards the bottom and undergo fermentation in that bottom layer. This yields beers that fall into the lager, pilsner category, and even your like Oktoberfest. So again, Saccharomyces is the major yeast, and then within that we have different species of Saccharomyces. So again, that's how we get the ones that are top fermenters versus bottom fermenters. But then even within that, we also have different strains, and so the different strains would give you different flavor profiles. One of the reasons why, even if they're using the same species of Saccharomyces, it could yield a very different tasting ale. Like, not all ales are the same, they all have different flavor profiles. So just as a refresher to remember some of the metabolism of Saccharomyces, when we look at the major producing, the big highlight pieces, we're going to have glucose metabolism, so we get glycolysis, and then pyruvate, and then through the breakdown of pyruvate, we can go through the TCA cycle and have production of ATP, but we can also utilize pyruvate in order to make ethanol. So that's going to be for our alcohol, but we can also produce a number of other organic compounds. So acetaldehyde, acetic acid. We can also get production of fatty acids, different phenol acids being broken down, esters being produced. We can get the use and production of amino acids, and we can also get diacetyl production in different sulfur components being produced. So all these different compounds are going to give us variability in the different flavors and affect the flavors that the consumer would end up tasting. So again, there's a range of different compounds that are going to be produced in addition to ethanol and carbon dioxide that will affect the flavor. And so there's a number of factors that will affect the concentration, how much of these different compounds are actually being produced. Some of that is because of the yeast strain being used. Other ones are because of, different variables. Pitch rate is when you're adding the microbes in, so the rate that you're adding in. So if you add it all at the same time, it's going to give you a different flavor than if that pitch rate is slowed down over an extended period of time. The temperature in which fermentation is occurring also will have factor, whether oxygen is present or not, how long the fermentation is allowed, also your carbon to nitrogen ratio, because that's what's going to feed your microbes, and any kind of maturation that is allowed to happen afterwards. So it's common in the distilled spirits is with like whiskeys to put it into like oak barrels. Well, that's going to change the flavor profile, and so some beers are actually put into wooden barrels, and again, some of those flavors from the wood actually gets incorporated into the beer flavor. So it's not just Saccharomyces that's doing the work. There's a lot of other fungal components and bacterial components when we're looking at beer, because again, depending upon what the end product, the process in order to get to the end product, and whether we have pasteurized the material to begin with, that is all going to end up contributing to what microbes are present. You can see in the middle here we've got the pitching yeast, so that's what I was referring to as the pitch rate. So you start with your grains and you're going to make a mash from that. You're going to heat that in the kettle, and then that's going to end up breaking down and releasing the sugars. So when you add the yeast, they have the sugars that are free from the grains so that they can ferment those. And then you have the additional conditioning, and so depending upon what microbes are present then, before packaging, can give you all these different flavor profiles of the beer. So it's not all beer is simple one organism undergoing fermentation. And as we've seen, different organisms are going to be able to ferment and produce different compounds beyond just ethanol and carbon dioxide. So there's some deviant fermentations, so deviating from the kind of conventional fermentation method that some of these larger commercial breweries would use. So one of those, and I've talked about these, is the cool ship. So the cool ship is where we have our wort, which is what's the cooling solution after you've done your mash. So again, this is what's going to have all these sugars being released from the grains available for microorganisms to consume and ferment. And so usually what happens is that they leave the wort out overnight, and this is in a shallow pan vessel, and so this is called the cool ship, hence the name. And so there's all this surface area where air is being exposed to the wort as it's cooling, and so this allows for any kind of the yeast and bacteria that are in the air at the site of the brewery to inoculate that wort, so that now what's undergoing fermentation is a combination of the yeast and bacteria, and depending upon the time of year, that's going to influence what is available. In some cases, that beer is then put into barrels. Other times, they're put into steel vats, and depending upon how long the company wants to leave it to ferment, they could wait for a couple months, or they could wait for years for a further development. What happens is, just like we see, in humans, where we get this succession, this changing, just like what we saw with the wine, where we see this changing of bacteria, microbes present. Same thing happens with these cool ships. So usually in the first month, enterobacteria are actually dominant, present. So they're going to undergo fermentation. They're going to be producing a number of different factors. So there's high amounts of alcohol, acetic, lactic acid. But then after about a month, what happens is we start to get some of those lactic acid bacteria in Saccharomyces present. So they actually then start to kind of take over the microbes that are present there, so they can undergo the alcohol fermentation. Usually they can, depending upon how much sugar is present, they usually dominate for 3 to 4 months. And then we get these Brettanomyces or Brent bacteria. So these ones kind of then move in, and they kind of finish off the flavor profile, if you will. So they actually will end up producing a number of aromatic compounds to the beer, and this includes even like fatty acids present. So that gives that beer the really characteristic kind of almost sour taste to it. But again, these are usually referred to as cool ships. So, or they're also referred to as wild fermentations. Another deviation is the mixed culture. So for the mixed culture, this is where instead of the beer being inoculated with a single strain of yeast, it'll actually get inoculated with a mixture. And this all depends on what the brewery wants to add into it. So they could add the traditional Saccharomyces, but they might add some lactobacillus and pedococcus bacteria in. And again, it gives it a different flavor profiles. So in Belgium, the Flanders beers are a known mixed culture, and then many of the sours are mixed cultures in the U.S. So some sours are wild ferments and cool ships, but I'd say the majority of the sours, traditional, they're very non-traditional, but the traditional sours would be a mixed culture where we have those lactobacillus bacteria in there. And that, the benefit of the mixed culture is it has a quicker fermentation process than what we see with those cool ships, because you're putting in known bacteria, a combination of known bacteria that are designed to ferment more quickly. So you don't have, it's not as long of a fermentation that you see with the wild ferments or these cool ships. Okay. They traditionally have a fruity, tarty taste to it because of the acids being produced. So some breweries will actually just sell this kind of young beer, but others will actually mature the beer longer. And again, the idea there is that those Brettanomyces and other wild yeast will actually further ferment the beer and develop the flavor. So then with, lastly, we're going to talk about mead production. So with mead production, the starting material is honey, and then you're adding water to that. That creates a mixture called the must. Additionally, you can add different spices and herbs and fruits to change the flavor profile. In most cases, it's Saccharomyces that's used, so just your regular baker's yeast, but there are some mead strains that are better at fermenting, that have been tested to be good mead producers, because there's different grades of mead. So you can have dry, you can have sweet meads, and so if your goal is to have a certain end product, you can actually purchase Saccharomyces strains that are more dependable on producing that end product. Okay. The process is similar to what we would see in winemaking. Because of the honey and not wanting to boil all the flavor away, pasteurization tends to be at slightly lower temperatures and shorter. If pasteurization doesn't want to be used, you can add sulfites into it, and the sulfites will kill the yeast. So that's one way that people get around with trying not to denature and change the flavor profile of the honey, is by adding these sulfates. And then during the fermentation, usually it's around 21 degrees Celsius, so room temperature. And so these can just be done on the tabletop. You do the basic setup is that you have a jar that you put your honey in, you add water, you heat the solution, and again, that's meant to kind of pasteurize, or you add these sulfate tablets to it, and that kills off the yeast, and then you add your yeast in there. Okay, and then that's allowed to ferment. You need to have like a venting top on it so that as the carbon dioxide builds up, you don't blow up the vessel. And then you'll go through, you can go through and siphon off the top, because any of the spices or fruits that you've put in will settle to the bottom. And the honey, you start to get kind of like a sludge on the bottom. So again, siphoning off what's on top to do some clearing of it. So usually with these meads, they're allowed to ferment for 6 months to a year, which gets you like a alcohol by volume concentration of 15 to 16%, but shorter fermentations can be done. They'll give you a lower alcohol content. And the alcohol content, and again, what type of mead it is, really depends upon the sugar concentration to begin with. So obviously, if you have a higher sugar concentration, the yeast can produce more alcohol. Further, this can be distilled or concentrated, and this will yield honey jack. So there's a number of factors that need to be looked at as far as spoilage. So with wines, what can happen is you can get these films of yeast and acetic acid bacteria that are present. So you need to be mindful, because that's going to change the flavor profile. So you can end up getting this heterofermentation of the lactobacillus, which is going to ferment the glucose and increase the acidity of the wine, which causes it to spoil. So it's not desirable to consume it. You can also get beer spoilage by these lactic acid bacteria. So I mean, some people would argue that these sour beers and cool ships are bad beers, but I don't know. I personally like the sour beers and that tardiness of them. So again, what one person's considering spoilage is different. In our next unit, we'll look at some of the pathogenic bacteria that could be an issue. And one of the reasons why pasteurization was developed was for the wine industry, because Louis Pasteur was concerned about the spoilage of wine and potential economic cost, but also potential of pathogenic bacteria. So he wanted to make sure that wine was safe for people to consume in France. So he developed pasteurization for that.